and welcome to Deeksha Karnataka YouTube channel and in the PU1 chapters of your Masterstroke series. So today we are beginning with the PU1 chapters of physics. So we are going to discuss units and measurement and motion in a straight line in today's lecture. So just have a look at the chapter summary. So we are going to discuss units, supplementary and derived units. We will also discuss significant figure and their rules. We will discuss error calculation. Also we will discuss dimension and analysis. Dimensions also we will discuss. So this is also included. And what else? We will discuss another chapter today, that is motion in a straight line. In motion in a straight line we will discuss speed and velocity, graphs, equation motion. Okay, so without any delay let us start. Units and measurement. Okay, now before at the beginning of mankind, okay, the measurement was almost not there. Then suddenly people think that okay, people are cheating on me, so we have to have some level of consistency. So if I am giving you 10 apples and you are giving me say only one orange bag, that means that kind of a cheating. Okay, so apples and oranges, maybe they are not similar in cost, but if I am giving you 10 apples, I am expecting 10 oranges back from you. So that's how the measurement started into existence, and people started measuring, okay, how much amount I am giving you, and in return how much amount I am getting. Okay, so in the past, you know that we had a barter system where exchange method was most popular. Then slowly monetary system came into existence, and then we started doing business in terms of weight, right, or mass rather. Okay, and slowly the measurement came into picture. Okay, so measurement is a fundamental process in science to quantify physical quantities. Okay, so to measure physical quantities or quantify means how much is this. Okay, if I say that how long is 1 kilometer is, so that is a quantification. Okay, we can exactly measure what is the 1 kilometer length, or what is the 1 kilogram of mass, or how much time is exactly 60 seconds. That can be measured. So to quantify some physical quantities. Okay, what is physical quantity will come to exist. We'll come to that as well. So that is called measurement. Okay, so measurement is the process of measuring. Next, physical quantity. Any quantity that can be measured and described by a number and a unit is called physical quantity. So physical quantity is something which can be measured and described by a unit. Okay, a value and an unit, then it is called a physical quantity. For example, mass, length, time, they are physical quantities. But the quantities which are not physical quantities, suppose you say that I studied for hours but I did not get enough marks, so that hurts me a lot. Okay, that can be some other context as well, but that hurts me a lot. How much is it hurting you? Can you measure that exact hurt that being put into your heart? Okay, that you cannot do that, right? So that is like a imaginary quantity, that is like a feeling. Okay, that you cannot measure. Okay, or if I say that if that was the case, I would have been very rich. So these things which are perspective, which are not actually be measurable, is called are not physical quantities. Okay, they are imaginary quantities. Physical quantities which physically exist, you can measure them, you can explain them using a value and an unit, then they are called physical quantities. Okay, when we are measuring any physical quantity, we are comparing it with certain basic arbitrarily chosen international accepted reference standard called unit. So what is this unit? Unit is basically something which is arbitrarily chosen. Arbitrarily means you cannot put a proper scientific logic to everything, that why this much length is 1 meter, or why this much weight is 1 kilogram. Okay, that was chosen, that was being done for centuries, even generation before us using that unit, and we are also using that unit Most of the units are arbitrarily chosen, not all of them, okay. Some of them are, there are some scientific logic behind them as well. So, but most cases, some common units that we use in our day-to-day life are arbitrarily chosen, because that historically people used to do that, okay, and it was internationally accepted. It cannot be arbitrarily chosen anything that you might think, okay. Suppose you want to define an unit of your own name, okay. So suppose your name is say X, and you want to define, okay, this much amount should be X from tomorrow, and everyone should negotiate using this value X. But that is not going to happen, because if you want to sell or buy something in that unit X, other people are people outside your domain, they will not accept that unit. They will say, I only exchange in kilograms, okay, I only exchange in US dollars, okay. Even if you are someone from India, I will not buy anything from you using Indian rupee. I only accept US dollar from you, okay. So that's how international trades happen, right? So we have a fixed currency, we have fixed amount, and based on that we do the trading. So basically it all came, the units, necessity of units, measurement, etc. came from the trading practices, okay. Because trading is not something that is happening today, it is happening for centuries, for thousands and thousands of years, okay. So because of this trading happens, we had to devise a way to trade with the people which are not part of that locality, which is those who are coming from outside, and but they are interested. For example, Indian spices, they are famous for throughout the globe, okay. And spice trading is one of the most common trading that happened in India in the past, right? So and many people came into India because of those spices, and so to trade them, we had to have some standard units, okay. This much amount you pay, or this much gold you pay, and you can take this much amount of spice from us, okay. That's how the trading used to happen, okay. The result of measurement of a physical quantity is expressed by a number accompanied by a unit. So whenever we say 1 kilogram, 1 is the number, kilogram is the unit, okay. So if I say 20 kilometers, 20 is the number, kilometers is the unit, okay. So basically it has to be two things. You have to, whenever you are defining an unit, it has to be first of all, it has to have a fixed value, and secondly, it has to be internationally accepted, okay. So for example, 1 kilogram, the mass of 1 kilogram is there in a museum in Paris, okay. If you ever visit there, you will find that there is a block of mass which is called 1 kilogram, which is kept in a perfect condition of 0 degrees Celsius. I think 0 degree or 4 degrees Celsius, I'm not sure, but the temperature is fixed, okay, and conditions are fixed, the atmospheric pressure is fixed, so that the mass of 1 kilogram is standard, okay. Similarly, the distance between two lines is considered 1 meter, which is also there in the museum, okay. The temperature, the condition has to be fixed, the material has to be fixed, okay. So and if you measure the distance between those two lines, you can get exact 1 meter length, okay. So those are already fixed. Next, so there are a few quantities whose units are fixed, okay. What are all those quantities? These quantities are considered to be primary quantities: length, time, mass, electric current, thermodynamic temperature, normal temperature, whatever temperature that we say, also called thermodynamic temperature, okay. Luminous intensity, something that you may not be super familiar, but it is also a fundamental quantity. And amount of substances. Amount of substances you have used in chemistry, right? These 7 quantities are considered to be fundamental quantities, okay. And they also are represented using certain symbols. Those symbols are called dimensions, okay. The dimensions of a physical quantities refer to the nature of the quantity in terms of the fundamental physical dimensions, okay. So fundamental quantities are these 7, and their respective dimensions are given in this chart, okay. So length is represented by L, third bracket, time is capital T, mass is capital M, electric current is generally A. Okay, for 99% of your life you will use A only. Temperature is K or capital theta. Capital theta is very less used. In old generation it was used capital theta, now it is used as capital K only. Luminous intensity is CD. CD comes from the unit candela. Okay, candela is the unit of luminous intensity. From there it is not cadmium, by the way, it is candela. Okay, and amount of substance is mole. And whenever you express a dimension, it is always represented using a third bracket. Okay, third bracket is common for all the dimensions. Clear? So here is a small table to remember. So here mass, current, okay, mass is kilogram, just for a representation. Okay. The unit, SI units, length, SI unit is meter, time is second, mass is kilograms, electric current is ampere, thermodynamic temperature is Kelvin, okay, luminous intensity I already mentioned, candela, and amount of substance is mole. So these are also the SI units. Okay, so for some of the quantities, as you can see, their units are exactly same as the symbol for their dimensions. Okay, except the first three. First three was more fundamental. It is there from the beginning. Later on, people realized, okay, these three are not the only fundamental quantities. There are few more quantities which are fundamental, and that's why they have added this another 4 quantities into the list. The total 7 quantities are considered to be fundamental quantities. Fundamental quantities means they are not dependent on anything. Okay, so current is not dependent on anything. Current is considered independent. These quantities are independent of each other and anything else. Okay, so these are considered to be fundamental quantities. Now there are 2 more units which are called supplementary units. Number 1 is angle. Okay, angle by dimension is a dimensionless quantity. Remember that even though it's an unit, by the method of dimension, it's a dimensionless quantity. So even though you can measure it, even though it has a value, even though it has an unit, fundamentally it is a dimensionless quantity. So if they ask you name a quantity which is a dimensionless quantity but it has a unit. Okay, so there are 2 quantities actually, this one and next one. So this is a dimensionless quantity, but still it has a unit, and the unit is radian or degree. Okay, radians or degree, which both of them are dimensionless quantity, and they are also has a unit. So, and one more important thing. So when you measure an angle, okay, generally if there is a curved line, okay, suppose this is a curved line, say curved line, length of the curved line is given by S. Okay, length of the curved line is given by S, just a second, and this distance is say given by R. Okay, so this distance is R and this distance is S. Then if this angle is theta, then S equals to R into theta. Okay, S equals to R into theta. Okay, so this is the relationship between the arc length, the radius of the circle, and the angle it makes. Okay, so if it's a curve, obviously it will have a center, okay, of curvature or radius of curvature basically. So if you join them back towards its center, okay, this is the radius of curvature and this is the arc length S. So you can calculate the exact arc length from this formula. S equals to R theta. Now remember, here theta is expressed in radian. Theta is expressed in radians. Okay, so this is the formula. So you can calculate theta equals to S by R. So if you know the arc length, if you know the radius of curvature, you can find the angle theta. Now if you see that it is basically a ratio of similar quantities. Arc length dimension is L, radius dimension is L, so it's a dimensionless quantity, but still it has a unit which is called radian. Okay, remember that, and obviously maximum value radian made by a circle. If you are given a circle, okay, and if they ask you what is the angle that it makes, so this angle is pi by 2. Okay, the total angle is pi plus pi, that is 2 pi. Total angle subtended inside a circle is 2 pi. Okay, So that's why the perimeter of a circle is 2 pi r. Okay, so 2 pi r, you can calculate 2 pi r is the perimeter. Same formula, actually everything comes from this formula only. Next is another dimensionless quantity which is called solid angle. Solid angle is basically, angle is a two-dimensional thing, solid angle is a three-dimensional angle. Okay, when you consider an angle in 3 dimension, it is called a solid angle, and in this case the surface is a part of a sphere. Okay, it is not a part of a circle anymore, it's a part of a sphere. If it is a part of a sphere, then if you join them back at the center of the sphere, okay, the angle it subtends is called solid angle. Okay. The angle it subtends is called solid angle, and it is denoted by capital omega. Capital omega, same as the symbol of resistance. Okay, so this is the symbol for solid angle. Solid angle is like a conical shape. Okay, it's like a conical shape. It's a three-dimensional angle. Its unit is steradian. Its unit is steradian. If you know the area, if you know the radius of the sphere on which it is the surface is located, then it is given by area divided by r square. Area divided by r square. It is also a dimensionless quantity. So both plane angle and solid angle are dimensionless quantity. Okay, both are dimensionless quantity. The angle subtended by a sphere at its center is 4 pi. So angle subtended by a circle is 2 pi, angle subtended by a sphere is 4 pi. So if you consider a sphere, okay, if you consider a sphere and if you go into its center, the total solid angle that it subtends is 4 pi and unit will be steradian. Okay, now you may have used some formulas like sine theta nearly equals to theta or tan theta nearly equals to theta for small value of theta, for small value of theta, okay, or cos theta equals to 1. These all formulas are valid when theta is expressed in radians. Remember that. These are all valid when theta is expressed in radians. These are all not valid for theta equals to degrees. They are only valid when theta is expressed in radians, not in degrees. Clear? Now let's move on to significant figures. So digits in a measurement that are reliable plus the first uncertain digit is called significant figure. Okay, significant digits are those digits obtained by a measurement and not by a calculation. Remember that significant figures are always comes from a measuring device, or when you are using a physical value, you are measuring it, then it is called significant figures. Okay, these are not part of a calculation. Okay, even though we use significant figure rules while calculating something, but the actual significant figure comes when you are using some measuring tape or some measuring device to get the exact value, then it is called significant figures. Now what is the meaning of this reliable plus first uncertain digit? What is the meaning of that? So suppose you have a measuring device. Suppose you are measuring a mass using some balance. Okay, we all have seen this kind of balance, right? Nowadays we use digital balance, right? Now suppose we are using some old school balance mechanism. We have some object over here and some mass, known mass over here. Okay, suppose it is showing, the scale is showing almost at the center, but not exactly at the center. Okay, slightly towards this, slightly heavier on the side of the object. Okay, that means suppose we have a 2 kg on this side and we have some object over here. Now when it is almost exactly at 0, when the scale is exactly at 0, then we can say that mass of this object is also 2 kg. right? So 2 kg on my left hand side, that means 2 kg on our right hand side. But in case, suppose we instead of having exactly 2 kg, suppose the scale is now tilted on this side. Scale is slightly tilted. That's how the people used to give you, right? So it is heavier on this side, you can take little extra from me, right? So now that, what does that mean? That the mass is not exactly 2 kg. 2 kg is guaranteed. 2 kg is guaranteed. That is the reliable. So 2 kg is the reliable mass. Okay, but it's slightly more than 2 kg. That means what we can say, maybe it is 2.1 kg. So this value is reliable. This one is reliable. And this one is, we are assuming or we are getting, okay, this is slightly more than, slightly more, okay, slightly more means this will be uncertain. This is the uncertain value. This can be 1, this can be 2, this can be 3, but because it's slightly more, we will take this as 0.1. Okay, similarly when you measure using a scale during examination, okay, when you measure using a scale, okay, especially during lab experiments, what you do, suppose this is 0, okay, and this is say 1, in between we have say 0.5, okay, and we have 1, 2, 3, 4, 0.6, 7, 8, 9. Okay, suppose this is the scale. While measuring, you found a result which is somewhere between 0.8 and 0.9. Somewhere between 0.8 and 0.9. Now sometimes it was said that it is better to take the smallest value. Smallest value is certain. Okay, so 0.8 is certain. Suppose you found the length is here. So 0.8 is certain. So it will be 0.8. But you say that, okay, this value is very close to the midpoint of 0.8 and 0.9. So we can write this as 0.85. So this value is uncertain, right? This value is uncertain because this is not exactly, we are not sure whether it is 0.5 or 0.6 or 0.4, but this value is something which you can say this is very close to this value. So this is the uncertain value. This one is the reliable value. Okay, this one we can say directly exactly it has to be greater than 0.8, right? So 0.8 is reliable. Anything slightly more than that will be uncertain. That is, according to our guess, according to our observation, we are getting this value. Now remember, all the values that we are saying over here are all coming out of experimental measurement, not from any calculation. For example, what is the meaning of that? Suppose you measured the length to be 0.85 say meter, okay, and you measured the breadth to be 0.5 meter. Now when you calculate area, area will be L into B. So this is a measured value. Okay, this is a calculated value. Okay, these two are measured. Okay, this is a calculated. So there, so when you calculate the area, the value of area will include significant figures obviously, but when we are saying that significant figure, that actually comes from the fact of actual measurement, not from a calculation. So after calculating the area, we have to consider the significant figures, but the result itself, we cannot say that it is a significant figure. Okay, that is not a significant figure of the area. Okay, that is the actual value of the area, considering significant figures. But the final result is not in significant figures. It is in it will be called as area itself. It will be not called area in significant figures. No. Okay. Now a few common rules that you need to remember while considering significant figures. Okay. Non-zero digits. All non-zero digits are significant. All non-zero digits are significant. For example, 123.45 has 5 significant figures. This is very common type of question where they will give you a number and they will ask you what is the significant figure. So if you know 123.45, so has 5 significant figures. Leading zeros. Leading zeros means zeros which are coming first. Okay, zeros that precede all non-zero digits are not significant. Any zeros which are coming before non-zero digits are not significant. For example, 0.0025 has only 2 significant figures, that is this non-zero digits. Okay, these zeros are not significant. Captive or sandwiched zeros, okay, or burgered zeros, okay. So between burger patty you have a zero in between, so those zeros are significant. Okay, zeros between two non-zero digits are always significant. For example, 1002 has 4 significant figures, even though there are 2 zeros, which is basically sandwiched between 1 and 2, so those 2 zeros are significant. Now, trailing zeros are in a decimal number. So trailing zeros in a number with a decimal point are significant. So if I say that 10.00, all zeros are significant. All zeros are significant. So here 50.00 has 4 significant figures. Remember that? So 10.00 means there are 4 significant figures. This is very tricky. This is very tricky, okay? So whenever there is a decimal point, okay, all zeros are significant. Next, trailing zeros in a whole number. Trailing zeros in a whole number with a decimal point are significant. So here also trailing zeros, as you see that here 100.0 has 4 significant figures. Trailing zeros in a whole number without a decimal point. So trailing zeros in a whole number without a decimal point are not significant. So 100.0 has 4 significant figures, but if I just write 100 or if I write 1500, these 2 zeros are not significant. Okay, it is only has 2 significant figures. Okay, so 1500 has only 2 significant figures. Very, very important. If you add a decimal, okay, so if I say that 1500 point, just a decimal, then all these zeros are significant. Okay, these are significant. But if I write 1500 only, then these zeros are not significant. Okay, very, very crucial to remember. If there is a decimal point means the device that we are using to measure the length or mass or whatever quantity that we are measuring is capable of measuring quantities after the decimal as well, but this is a very specific value. We are this is the exact value, so that means these zeros are significant. If zeros are not, if there is no decimal, that means it's just a value. Okay, we do not know exact capability of the device measuring the this value. That means only 2 significant figures. That is the exact meaning of it. Okay, you don't need to remember the meaning, but you have to remember that if there is a decimal point, zeros are significant. If there are no decimal points, zeros are not significant. Very, very important point to remember. Exact numbers, for example, 1 dozen. Okay, exact numbers are infinitely significant. Okay, so if I say that 1 dozen, 2 dozen, okay, exactly, say exactly 15 or exactly 10, they are infinitely significant. Why so? Because if I say that 12 dozen, 1 dozen exactly means 12. That means after a decimal, if you put 1, how many zeros does not matter, no matter how many zeros are there, okay, it will still be exactly 12. It will not be 12.001. Okay, so that means because it's a exact number, that means it can go, if after if you can put a decimal and you can write infinite number of zeros after that, that's why an exact number is infinitely significant. An exact number is infinitely significant. Next, scientific notation. Scientific notation is also important. All digits in the scientific notation, number written in scientific notation are significant. So for example, so if you write this number, these numbers, all the numbers are significant. 10 to the power values are not significant. Okay, 10 to the power values are not significant. These 3 or 4 are not significant. Okay, only this 2.30 are significant. Choice of unit. A choice of unit or changing the unit does not change the number of significant figure. For example, 2.03 centimeter has 4 significant figures. It won't change if you switch to into meter. Okay, so if you change the unit, the significant value does not change. Okay, significant digits does not change. So whatever significant digits was there in centimeter, no matter if you convert it into meter or kilometer or decimeter, the number of significant digits will not change. Number of significant figure will remain unchanged. So it is independent of units. Next, rules for calculation. This is also very, very important. Addition and subtraction. So the result should have the same number of decimal places as the number with the least number of decimal places. So when you are adding two numbers, okay, you need to consider significant figures also. Okay, so for example, 12.11 plus 0.2. 12.11 plus 0.2, if you see that here we have only one decimal point. Okay, here we have how many? 2 decimal points. So out of these two numbers, who is smallest? Smallest is 1. So the answer will also have only one decimal point. So basically what you have to do, how to do that? Suppose we have 12.34 plus 0.5. Suppose we are doing this addition. So first thing you have to approximate this number into the one decimal point, that is 12.3. okay, and then add this number, that is 0.5, then you get 12.8. okay, this is one method, or you can simply add that, okay, 0.84, and then you say that there is only one decimal point, so we can drop this 4. okay, we have to consider and ignore this 4, right? So 0.5, so 12.84, so you can drop this and answer will be 12.8. okay, we will see that further in rounding off rule. In some cases you have to round off and the answer slide can be changed based on the rounding off. So after adding that, you have to round off to the nearest smallest decimal number. okay, in case of multiplication, again the result should have the same number of significant figures as the number with the least number of significant figures. So for addition, decimal point is important, not the total significant figures. In multiplication, total significant figure is important. Both cases we take the least. okay, so here we take the least with the decimal number. In case of multiplication or division, we take the least significant figure. okay, so for example, 4.56 into 1.24. So this one has how many significant figures? 3. This one has how many significant figures? 2. So our answer should also have 2 significant figures only. So this is a rule for multiplication. Normally, obviously, we do not follow this exact rule, but in exam, if they say that this is multiplied by this, what is the answer according to the significant figure rule? Okay, you have to multiply them and you have to find the least. So minimum 2 digits are there, so you have to identify a number with 2 significant figures. okay, that's how you can even guess the answer. okay, because they will give you same answer with different significant figures. You don't, if you see this kind of question in the exam, the question is not about the exact multiplication, but the answer which denotes the correct significant figure. So they will suppose they will give you 4.56 into 1.4. Suppose they will give you answer 6.32, 356 or 6.4, or they will give 6. okay, so which one is correct? So we know that here we have 2 decimal number over here, so 2 significant figure over here. So our answer should be 2 significant figures. So only this one is 2 significant figures. This one will be the answer. So you don't need to do the multiplication to check whether it will be 6.4 or 6.356, but you have to calculate. Okay, this is the significant figures. That means from the significant figure, answer will be 2 significant figure only. Okay. If the digits to be dropped, now rounding off. Now how to round off a number? Suppose we have a number, say xx, yz. Okay, suppose this is a number. Okay, x. Okay, let me change the number. Sorry. Say x, y comma Z Q. Suppose this is there is a number like this. Now if you want to drop this number, you want to round off this digit into 3 significant figure. Okay, suppose round off this to 3 sig fig. So how to do that? So you can simply write xy dot z. Okay, but that may not be correct, that may be correct as well. Now based on this digit which you are dropping, that is you are removing, you are not writing in this equation, okay, whether this number is greater than 5 or less than 5, you can have 3-4 different rules. Okay, so what are those? If the number is less than 5, you can simply drop that number. Okay, you can simply drop that number. So if q is less than 5, then the answer will be xy comma z, xy point z. You can simply drop. So for example, here we had 12.43 and we are rounding off into 3 significant figures. So that means we are dropping this 3. This 3 is less than 5. So simply answer will be 12.4. If the number is greater than 5, then what you have to do? If the number is greater than 5, then your answer will be xy point z plus 1. Okay, if q is greater than 5. So for example, if the number is 12.46, this 6 is greater than 5. So it can be 6, it can be 7, it can be 8, it can be 9. Okay, does not matter, as long as the number is greater than 5. When you are rounding it off, it will be 12.5. So you have to increase this by 1. You have to increase the number by 1. Okay, now what would be the case if the number is exactly 5? If the number is exactly 5, then you have to consider 2 more rules. This is tricky. These 2 are easy. Obviously, we are using it in our day-to-day life, almost every calculation. But if it is exactly equals to 5, then the calculation can be tricky. Okay, if the number that we are dropping, the number before that, if the number is odd, okay, if the preceding digit is odd, then we increase it by 1. Okay, so if the number is say 12.35, this is an odd number. Okay, we are dropping this 5. Okay, it is neither greater than 5 nor less than 5. It is exactly equals to 5. And the number before this is odd number. We increase it by 1. Our answer will be 12.4. But when you are dropping a number, if that number preceding it is even number, for example 12.45, 4 is an even number. Okay, so in that case, after the rounding off, it will be 12.4. We do not do anything. So if the last number is 5, exactly equals to 5, the number that we are dropping, if that number is 5, remember that your final answer should be an even number. Okay, your final answer should be an even number. That's how you can remember. Okay, if I am dropping a 5, it should be an even number. If number is after dropping, if the number is already even, we don't do anything. If the number after dropping is odd, then we increase it by 1. So it will be 12.4. Okay, remember that. Your answer is always even number. So this is also 12.4, this is also 12.4. Even though the number that we started with are different. Okay, this is very, very tricky. Other than that, all the rules are very simple. Let's move on. Now, uncertainty based question. This example is exactly there in your NCERT. So what is the meaning of uncertainty? Uncertainty is something which the digit that we are measuring, the last digit that is not certain. Okay, how much error is there? That is a measure of error. Okay, uncertainty is a kind of measurement of error. Okay, so uncertainty should be converted into percentage first and then added. Okay, so for example, how the uncertainty is written. So for example, if you see that here length is measured of certain quantity, which is measured as 0.3, it is a certain value, plus or minus 0.003 centimeters. So this is called uncertainty. Okay, exact definition, exact understanding of uncertainty is not super required because it is not part of the syllabus, but these kind of calculations are there in your book, and this value is called uncertainty. Uncertainty means like Heisenberg's uncertainty principle. Similarly, the value is not exactly fixed. You cannot exactly say whether it is a 0.3 or 0.303 or 0.2907. Okay, 0.2907. It is basically varying. It is varying between those two digits, 0.2997 or 0.303. So it is actually between these two values. Exact value, obviously 0.3 is known, but whether it is a plus or minus, exactly not known. So this is called uncertainty. So between these two ranges, the value changes. Okay. So this is called uncertainty in the measurement. Okay, based on different cases, uncertainty can appear. Okay. So length is given by this value and breadth is given by this value. Okay, 6 plus or minus 0.03 centimeter. Now if they ask you what is the area, how to calculate the area, obviously you can normally what we do, we multiply length and breadth to calculate the area, that is 1.8, but in this case you cannot do that. So how to do that? How to achieve that? First of all, you have to convert this number into percentage using this value. How to convert it into percentage? So here uncertainty or delta L, uncertainty is represented by delta L. So delta L is obviously 0.003 and actual length was given by 0.3. Okay, so you divide it and then you multiply with 100. This is the percentage error. This is called percentage error. So decimal is gone. So you get 0.03 multiplied by 100, you get 3/3%, that is 1%. So error is 1% or uncertainty is 1%. Okay, in terms of breadth also you have to do the same thing. So delta B by B. So delta B is 0.03 divided by 6 into 100%, that is 3/6%, that is 0.5%. Okay, so as you can see, the uncertainty in length is 1%, uncertainty in breadth is 1.5%. Now when you calculate the area using the formula, okay, these two will be usually exactly how you calculate the area. Okay, so length into breadth, so 0.3 into 6, that is 1.8. Done. When you calculate the uncertainties, here you have to add them. Okay, here you have to simply add these two quantities. So it will be plus and minus 1.5%. Now 1.5% of what? 1.5% of this. Okay, now from percentage you have to go back to the number. How to do that? So the L into B is 0.3 into 6, that is 1.8, and from there you can calculate the percentage. So delta area by area equals to 1.5%. I don't know why it is not working. Just a second. So this will be 1.5%. It will be 1.5%. Now you have to cross multiply to calculate delta A. Percentage means 1.5 by 100. Obviously, when you convert into percentage, you multiply by 100. When you go back from percentage to fraction, you divide by 100. So delta A is actually area into 1.5 by 100. Okay, that is 1.8 into 1.5 by 100, which will come out to be 0.03. Okay, so it will be 0.03 centimeter square. Okay, so this is how you calculate the uncertainty. Remember that generally if it is given in terms of percentage, you can simply add it to find the uncertainty. Okay, this is a slightly longer complicated problem given in your textbook, but remember that how to calculate or how to add the uncertainties, it always has to be converted into percentage and then you can add it. Okay, error assessment is not there in your syllabus. Now one important question: if P, Q and R are physical quantities having different dimensions. So their units and dimensions are different. Okay, which of the following can never be a meaningful quantity? Suppose we have, say, a quantity A which is measured using kilograms. We have another quantity, say B, which is measured using, say, meters, and another quantity, say C, which is measured using seconds. For example, I am taking three fundamental quantities. Now, if I say, what is the quantity if I add A plus B? So if you see that here A is in kilograms, B is in meters. Can we add them? Can we add kilogram plus meter? So this does not make any sense. This quantity does not exist. So any two quantities having different dimensions, they will not exist in nature. Okay, so I have taken three fundamental quantities to explain it better. So remember that when you are considering quantities, okay, they can be fundamental, they can be derived as well. Derived means obviously any units which are not fundamental are called derived, which is basically sum or multiplication of, which are multiplication or division of fundamental quantities are called derived quantities. So two different quantities cannot be added. Two different quantities cannot be added. You can add only if their dimensions are same. So if I say that x plus y equals to z, then dimension of x will be automatically be dimension of y and automatically be dimension of z. Okay, so these three, if I say that x plus y is equal to z, then x dimension, y dimension and z dimension, they will also be equal. Okay, we can, however, multiply these dimensions. So we can, however, say AB by C, kg meter per second, okay, unit of momentum. So this is a dimension for momentum. So multiplication, division, etc. is possible. When you are considering two dimensions, their multiplications and division is possible, but their addition, direct addition, is not possible. So if you see here directly which quantity is not possible, if you see that here P minus Q is there. P minus Q, P and Q both are of different dimension, so you cannot subtract two different quantities. Okay, you cannot subtract two different quantities, that is not mathematically possible. So kilometer minus meter, kilometer minus second is not possible. Kilometer minus meter is possible. Okay, you can convert kilometer into meters and you can convert it, but dimensions are different, means P and Q have different dimensions. So this operation, this negative operation is not possible. So this is not possible. So this quantity is dimensionally not possible. Now this quantity is obviously possible, as I mentioned. Now you might say, sir, then how can this quantity be possible or this quantity be possible? They are also negative sign, but here if you see that they are not directly simply they are not subtracting from each other. Okay, if this quantity, say PQ minus Q square was there, then this is not possible. Why? Because if you take Q common, you get P minus Q. So this quantity is not possible. Simple subtraction between two fundamentally different quantities are not possible. But when you multiply a third quantity which is completely different from there, P and R may have same dimension as Q square. Okay, P into R may have same dimension as Q square. Okay, because these two are completely different quantity. So these two quantity, if you multiply them, they can have a dimension equal to Q square, right? For example, G into H, okay, gravitational acceleration into height, that can give you a dimension of velocity. Okay, so GH equals to Q square can be still possible. Okay, so that is a well accepted quantity. Similarly here also, if you see P into Q minus R, P into Q can give you a quantity which is dimensionally P and Q can have a dimension same as R, which are different in dimensions. Okay, so these quantities can have different dimensions, right? So these two are possible, but this one is not possible because of straightforward difference. Okay, and this is a KCET 2019 question. This kind of questions are common, very fundamental, basic question. Okay, so be prepared for those kind of questions. Obviously, we will practice more PYQs in our PYQ session. Now let's continue with the second chapter, motion in a straight line. Now let us complete the remaining chapters quickly. Motion in a straight line. Just a second. So first, obviously, is velocity, speed and acceleration. So these are the three quantities that you must know. So the instantaneous velocity is given by dx by dt. Obviously, how fast an object is moving with respect to time is velocity. Okay, time rate of change of displacement is also called velocity. But when it comes to instantaneous velocity, it depends on how fast the object is moving over a given period of time. That is called instantaneous velocity, and it is given by dx by dt. Now if you are given a displacement time graph, okay, x versus time graph, okay, if this is the graph, then dx dt basically represents, let me change the color. So basically dx by dt gives you the slope of the graph. Okay, so this is dx, this is dt, and dx by dt basically gives you the slope of the graph. So at a certain point of time, if you know the slope, you know the instantaneous velocity. Slope of the displacement time graph at any given instant gives you the instantaneous velocity. Instantaneous acceleration is rate of change of velocity. So basically, in other words, you can say that this is nothing but this is equals to double derivative of displacement. Okay, so d2x dt square. So if you, similar way, if your velocity time graph is given, slope of a velocity time graph gives you acceleration, and average velocity is very common, total distance traveled by total time taken. Right, now let's move on. Few graphs that you have to remember, because the graphs are very common, and many times graphs are asked in the exam. So xt graph, xt is displacement time graph. The slope of displacement time graphs gives the instantaneous velocity. Velocity time graph, area under velocity time graph represents the total distance traveled, and slope of velocity time graph gives you the acceleration. So as I mentioned, okay, now area under the xt graph does not gives you anything. Vt graph, area under the graph means what is, suppose this is velocity, this is time, so this represents area under the graph. Okay, we have applied that in your PU1. If you remember, different expressions for velocity, then total distance traveled, we calculated using this graph. Okay, and one aspect of the derivation was that area under the graph gives you the displacement, right? Or total distance traveled. Now in case of speed time graph, it is total distance traveled. In case of velocity time graph, it is the displacement. Okay, slope of velocity time graph gives the acceleration. Now acceleration time graph, area under acceleration time graph represents the change in velocity. This is very important. So change in velocity is given by area under acceleration time graph. Now there are three different graphs for position time graph. Okay, first of all, when acceleration is positive, acceleration is negative, acceleration equals to 0. So these are the three graphs which represents three different cases. These cases are very, very important. So for positive acceleration, when the acceleration is increasing with time, the xt graph will be increasing as well. Okay, it can be, it not necessarily like that, it can be like that as well. Okay, the graph should be curved and it should increase with time. Okay, it should increase with time so that you can calculate the exact slope. If you can calculate the slope, you can calculate the velocity and correspondingly acceleration as well. Negative acceleration, the displacement decreases with time. Okay, and if it is a straight line, graph, acceleration is 0. And if it is a constant velocity, if the object is at rest, then this will be the graph straight. Okay, it will be parallel to time axis. If the graph is parallel to time axis, velocity equals to 0. velocity equals to 0. Constant velocity, it will be a straight line graph. Okay. Now when the object, if you drop an object at some height, okay, and if only force due to gravity is acting on the object, then it is said that object is at free falling state, okay, or it is a free fall. Free fall means object is falling under the influence of gravity. That motion is called free fall. And in case of free fall, if you plot the graph of velocity versus time, then the graph will be like this. Now why this is a negative graph, why the line is negative? Okay, because as the velocity object is falling downward, okay, its velocity in the downward direction increases. Velocity in the downward direction increases. So downward direction means the distance from the surface of the earth is decreasing. That's why it considered as negative direction. Okay, anything which is falling towards earth is negative, anything which is going upward is considered positive. Similarly, the distance traveled with respect to time is actually like this. Okay, and it is slowly starting from some height and going towards 0. Okay, ignore this, so it will be having some positive value and slowly it will going towards 0. This might be true when the object is going into the surface of the earth. Okay, so this, 0 surface is the earth surface, and if the object is going into the surface, inside the surface, suppose you dropped some stone inside say a mine, okay, there is an open mine, you drop an object, or a well, okay, well, you have seen well, okay, water wells. So if you drop a stone inside a well, this graph will be like this. Okay, the distance will be negative inside the surface of the earth, right? So this is the general graph for displacement, this is general graph for velocity for free fall. Okay, now equation of motion, very important. There are few equations of motion that you need to remember, obviously very common. We are using all equations of motion in multiple times. So V equals to U plus AT. V is velocity, U is initial velocity, A is acceleration, T is time. S equals to ut plus half at square. This is also very common equation. S is the displacement, u is initial velocity, a is acceleration, t is time. Okay, and v square equals to u square plus 2as. Now all these three equations are interlinked. Okay, interlinked means you can use one equation to go back to any other equation. So basically these three equations are not very independent. You can go from one equation to another very easily. But why do we need three equations? Based on what are the values that is given to you and what are the values that you want to calculate. So based on that you can use any one of the three equation of motion. Out of that, this is considered to be most fundamental. Okay, this equation, and other equations can be proved from this equation, right? Now distance traveled in nth second, this can be sometimes handy if you know. If you don't know, does not worry, you don't need to remember this or memorize this formula. So distance traveled in nth second is nothing but suppose total distance traveled in n minus 1 second and distance traveled in total distance traveled in nth second. This is called distance traveled in exact nth second. Okay, that means suppose you are moving in a car. Okay, you are moving in a car exactly in the 10th second. 10th second means that 1 second. Between 9 and 2:10, that exactly 1 second how much distance you have traveled. To calculate that, we generally use this formula. Okay, so this is the formula to calculate the distance traveled in nth second. You use these formulas for n and n minus 1 and then find the difference between them. That will give you the exact distance traveled in the nth second. Okay, so this is a shortcut formula. Sometimes it can be handy to save some time. That's it. But mostly this formula came in JEE. In KCET, I think only once if you had used this formula would have been some time saving for you. Otherwise not super important. As I mentioned, this formula is obviously, these two formulas are obviously important, and based on what values are given to you and what you are trying to calculate, you need to use the exact formula. Let's see one question from 2025. two stones being fall from rest from the same height with the second stone starting to fall at delta t seconds after the first falls from the rest. Okay, the distance of the separation between the two stones becomes capital H t naught seconds after the first stone starts its motion. Then t naught is equal to, so this is slight printing error, this is t naught, okay, this is t naught, not to, okay. So two stones being fall from the rest at the same height. So we have, suppose a tall building, okay, we drop one stone from the rest, okay. First stone was was allowed to fall, okay, and after delta t seconds, you allowed the second stone to fall from the same height, okay. First stone already started to fall, and after delta t seconds you allowed the second stone to fall, okay. Now it says that after some time t naught, okay, after some time t naught, after the first stone starts, so after t naught of the first stone, okay, the height that these two stones have achieved, say, is capital H, okay. Now they asked you what is the value of t naught, okay. So obviously when you drop the first stone, it started from the rest, so what is the total height or total distance traveled by the first stone, say h1, total distance traveled by the first stone h1 is given by half g t naught square, okay. This is the total distance traveled by the first stone. Now what about the second stone? Second stone covered, say this height is say h1, this height say h2. Second stone actually started to fall after delta t second, okay. So the same formula will be same, only here it will be t naught minus delta t whole square, okay. Only this will be the difference. Why? Because obviously the second stone started delta t seconds after the first stone. Equation of motion, first equation is obviously very simple, because the time t naught is given in terms of first stone, so first stone is total time is t naught. For the second stone, because the second stone starts after delta t seconds, the time will be t naught minus delta t for the second stone. So in the question it is given that h is actually h1 minus h2. H is equals to h1 minus h2. So this value is given in the question, and from there you are supposed to calculate this t naught value, okay. So now let's start. So h equals to, obviously half g will be common, so half g, that is g by 2, it is common, and in bracket we can write t naught square minus t naught minus delta t whole square, right. Now we have to simplify. So 2h by g equals to t naught square, that is a square minus b square. We can apply that, a plus b. So a plus b is t naught plus t naught minus delta t into t naught minus t naught plus delta t, right. So obviously t naught cancels, and you can write this as 2 t naught minus delta t into delta t, okay. Or you can write this as 2h by g into delta t equals to 2 t naught minus delta t. Now obviously obviously T naught is much larger than delta t. Delta t is very small time. So you can ignore this delta t. With respect to T naught, delta t is very small. So you can ignore this delta t and you can write 2 T naught equals to 2h by g into delta t, or 2 cancels and you can say T naught equals to h by g delta t. So correct answer is option D. Okay, h by g delta t. So this is the correct answer. So obviously not super simple, not super difficult as well. So if you know the formula, how to solve it, do step by step method, and at the end just ignore this term because delta t is obviously, because it's a small distance, it is denoted by delta t. If it is a very large distance, it does not make any sense, the problem does not make any sense. Okay, so obviously delta t you can ignore.